In quantum chemistry, methods like Hartree-Fock and density functional theory treat electrons explicitly. While this provides extraordinary accuracy, it introduces a severe mathematical penalty. As you add electrons to a system, the computational cost scales exponentially. This diagram illustrates the resulting divide. On the left, we see the quantum bottleneck, where explicit electron modeling works perfectly for small molecules. On the right is the missing complexity. Real-world systems require us to simulate millions of atoms over extended timescales. Even with powerful supercomputers, a standard DFT calculation maxes out when a system crosses a few thousand atoms. The sheer volume of continuous electron-electron interactions becomes too massive to compute. Biological membranes and synthetic polymers do not function in a vacuum, nor do they function as tiny fragments. To understand how a drug physically binds to a cell, or how a plastic flexes under mechanical stress, we must track the motion of millions of interacting atoms across nanoseconds or even microseconds. To bypass this computational bottleneck and simulate macromolecular behavior, we have to make a radical structural compromise. We must completely abandon the explicit calculation of the electron. Instead of relying on a fluid, probabilistic cloud of subatomic particles, we impose a rigid mechanical geometry. In molecular mechanics, the electron wave function is no longer the central object of our calculations. It is entirely replaced by the potential energy function. We adopt a strict mechanical metaphor. Atoms are treated as discrete solid particles with exact physical positions. The chemical bonds connecting these atoms act like physical springs. The forces that govern how the molecule moves and bends are determined by empirical mathematical formulas, known collectively as force fields. By ignoring subatomic electronic movement, the math simplifies drastically. Treating a molecule as a purely mechanical system reduces the computational load, allowing us to stretch our simulation capacity from thousands of atoms to tens of millions. This master equation calculates the total potential energy of that mechanical system. It determines the molecular energy as a function of the exact atomic positions. The total energy is the sum of 4 discrete components: bonds, angles, torsions, and nonbonded interactions. This diagram breaks down how these components are modeled. Bond stretching and angle bending act like physical springs, sharply increasing energy when forced out of equilibrium. Torsional rotation describes the energy to twist around a central bond, using periodic functions to model stable conformations. The model also accounts for non-bonded interactions across space, split into van der Waals and electrostatics. The Leonard-Jones potential balances weak dispersion attraction with a massive repulsive spike to prevent simulated atoms from overlapping. These equations alone are incomplete. They require specific numerical parameters, like the exact equilibrium length of a carbon-oxygen bond, or the specific partial charge of a nitrogen atom. We obtain these values by calibrating the classical model to match rigorous experimental data. This leads to a critical rule. A force field is only reliable when used strictly within the chemical domain for which it was parametrized. A force field calibrated for liquid organics will fail if applied to a metal-organic framework. Without explicit electrons adjusting in real time, classical simulation accuracy depends entirely on the precise quality of its imported parameters, rather than first principles calculation. This rigid mechanical blueprint has a severe structural limitation. Because chemical bonds are hard-coded as predefined springs, ordinary molecular mechanics cannot describe a chemical reaction. As listed on the right side of this graphic, the classical engine breaks down entirely when we try to simulate bond breaking, bond formation, electron transfer, or excited states driven by photochemistry. To solve this, computational chemists developed the QM-MM architecture. As this diagram illustrates, it functions like a highly focused microscope. We treat the chemically active region with quantum mechanics and surround it with a vast environment managed by classical molecular mechanics. This graphic directly compares the two halves of the system. The QM region handles the atoms directly involved in electronic changes, like a catalytic metal center or the exact site where a bond is snapping. Here we run explicit electronic methods like density functional theory. The MM region maps the massive surrounding environment, such as the full protein scaffold or the bulk solvent. By deploying faster classical potential theory, it provides the necessary structural and electrostatic influence on the active site without crippling the computer. This hybrid approach is crucial for biology. In an enzyme, localized quantum chemistry is physically shaped and electrically stabilized by the massive surrounding protein structure. Integrating these two regimes introduces a major computational hurdle. How do the rigid classical surroundings and the dynamic quantum core communicate forces to one another? This chart outlines 3 embedding schemes. In mechanical embedding, the quantum calculation is blind to surrounding point charges. In electrostatic embedding, mechanical charges are included in the quantum Hamiltonian. In polarizable embedding, the environment dynamically responds to the shifting quantum electron density in real time. A secondary problem occurs when the boundary line between these regions cuts directly through an existing covalent bond, like severing a protein side chain. As shown here, this leaves the quantum region with an artificial dangling bond that will ruin the mathematical calculation. The standard solution is a link atom. A placeholder, typically a hydrogen atom, is artificially inserted at the boundary line to cap the quantum region. This cleanly completes the valence, so the explicit electron calculation resolves properly. Managing this intersection is crucial. The accuracy of the coupling architecture is just as vital as the rigor of the quantum method itself. Look at the center panel of this biological application chart. In enzyme catalysis, QMMM isolates the precise moment of bond cleavage using quantum math, while classical mechanics calculates how the thousands of surrounding atoms fold around the pocket to make that reaction possible. We see the same architecture applied to material science in this OLED diagram. Quantum mechanics calculates the exact emission energy of the central chromophore, while the mechanical force field models the complex structural disorder of the surrounding solid film matrix. This matrix summarizes the computational trade-off. Pure quantum mechanics handles electrons and bond breaking perfectly, but fails at scale. Pure molecular mechanics operates at massive scales with extreme speed, but cannot compute reactions. The hybrid method balances the two. Stripping away the explicit electron and reducing atoms to simple spheres and springs is the only way we can generate the immense computational scale required to observe bulk materials and complex biomolecules over meaningful spans of time. Ultimately, the classical force field and the QMMM architecture act as practical tools for applied chemistry. They allow us to calculate the invisible interactions of the microworld and project them accurately into realistic, massive